In mathematics, Suslin's problem is a question about totally ordered sets posed by Mikhail Yakovlevich Suslin and published posthumously. It has been shown to be independent of the standard axiomatic system of set theory known as ZFC. The statement can neither be proven nor disproven from those axioms. Un ensemble ordonné sans soutenir qu'une telle out ensemble de ces intervalles n'empiète pas les uns sur les autres est au plus d'énumérables. Est-il nécessaire un continu linéaire, a ordered set without jumps or gaps and such that every set of its intervals not overlapping each other is at most enumerable? Is it necessarily in linear continuum? The original statement of Suslin's problem from formulation. Given a non-empty totally ordered set R with the following four properties. R does not have a least nor a greatest element. The order on R is dense. The order on R is complete, in the sense that every non-empty bounded subset has a supremum and an infimum. Every collection of mutually disjoint non-empty open intervals in R is countable. Is R necessarily order isomorphic to the real line R? If the requirement for the countable chain condition is replaced with the requirement that R contains a countable dense subset, then the answer is, indeed, yes. Any such set R is necessarily order isomorphic to R. The condition for a topological space that every collection of non-empty disjoint open sets is at most countable is called the Suslin property. Implications. Any totally ordered set that is not isomorphic to R but satisfies, is known as a Suslin line. The Suslin hypothesis says that there are no Suslin lines. That every countable chain condition dense complete linear order without endpoints is isomorphic to the real line. An equivalent statement is that every tree of height omega-1 either has a branch of length omega-1 or an anti-chain of cardinality. The generalized Suslin hypothesis says that for every infinite regular cardinal kappa, every tree of height kappa either has a branch of length kappa or an anti-chain of cardinality kappa. The existence of Suslin lines is equivalent to the existence of Suslin trees and to Suslin algebras. The Suslin hypothesis is independent of ZFC. Jetch and Tenenbaum independently used forcing methods to construct models of ZFC in which Suslin lines exist. Jensen later proved that Suslin lines exist if the diamond principle, a consequence of the axiom of constructibility V equals L, is assumed. On the other hand, Solovay and Tenenbaum used forcing to construct a model of ZFC in which there are no Suslin lines. More precisely, they showed that Martin's axiom, plus the negation of the continuum hypothesis, implies the Suslin hypothesis. The Suslin hypothesis is also independent of both the generalized continuum hypothesis and of the negation of the continuum hypothesis. It is not known whether the generalized Suslin hypothesis is consistent with the generalized continuum hypothesis, however, since the combination implies the negation of the square principle at a singular strong limit cardinal. In fact, at all singular cardinals and all regular successor cardinals, it implies that the axiom of determinacy holds in L and is believed to imply the existence of the inner model with a superstrong cardinal.